Hey there, thank you for tuning into CMTEQ channel in this series of tutorial on IDMT relay settings. So as you can see, this is tutorial 9 in this series of tutorials. So if this is the first time you are tuning in, I recommend that you watch the previous tutorial in this series where I have extensively covered this topic. Each tutorial adds a new complexity into the calculation. This is why it is important to catch up with the previous tutorial so you can keep up with the pace. Great. So having said that, by the end of this tutorial, you will improve on your understanding of IDMT relays settings calculation. So make sure you pay close attention to the tutorial. As you can see here, we've got a schematic representation, a schematic diagram representation of an IDMT relay set, with one of the key components here being the aluminum disc and the plug bridge. Obviously, the tripping circuit is also one of the very important elements in an IDMT relay here, as you can see in the physical representation of the real device. Great. So before we start discussing the problem statement at hand here, let's just lay the groundwork here. What exactly is an IDMT relay? Well, to define it, an IDMT is basically an inverse definite minimum time relay, which is a type of protection equipment or a protection relay used in power system to protect against overcurrent. So the keyword there is overcurrent, right? Because in power system, we do not want to allow an overcurrent to basically flow into the network, because that will disrupt the power system. Because one of the key objectives of an electrical network is to provide continuity of supply. The power system must never be interrupted. That is why even when there are planned maintenance, there is always contingency plans in place to ensure that the consumers are always being supplied with electricity. Great. So one of the keywords that we've also mentioned about this IDMT relay is the word inverse and minimum time. Now let's first deal with the word inverse. Now the reason why it is inverse, because it operates in an inverse manner. What does this mean? This basically means the higher the fault current, which we're going to see when we start solving this problem here. So the higher the fault current, the faster your IDMT relay is going to trip to basically protect your circuit. Now, what causes the tripping to trip faster is this disc here. As you can see, there is a disc there. Now, this aluminum disc is going to turn faster when there is a higher fault current detected on your bus bar. Okay, that is why it is an inverse. So it's operating inverse way. Higher current, faster trip down. Now, the other keyword that is also there is the minimum time. Now look at it. It operates faster, but there is also a minimum time. As we start solving this problem here, we're going to talk about actual tripping time and operating time. Okay, so there is a minimum time in which the relay has to operate. So it's not going to trip before that time elapses. Now, this is important for relay coordination, because if that time is not taken into account and you've got a bunch of IDMT relays on your network, so what's going to happen is each one of them might start tripping at the same time, and all of a sudden all the bus bars are going to be out of power. So they have to allow coordination. One has to trip after the other based on the level of the fault or whether the fault hasn't been cleared yet. So now that we've covered a little bit about how these IDMT relays basically operate, now let's go ahead and start solving this problem. Now before we do that, please make sure you subscribe to CMTEQ channel and give this tutorial a thumbs up. It is important to note that CMTEQ channel is one of the top channels providing power system tutorial on YouTube. So ensure that you stay tuned. Great. So the background of this problem statement here is that you've got a power system network that has been already erected. You've got your substations and you've got a couple of power transformers that have been installed in your substations with multiple feeders feeding into your distribution network. Okay, And you also now have IDMT relay settings that have been installed to coordinate with circuit breakers so that they can provide protection onto your network. Okay, so now your problem here is that you need to find the correct settings that you can implement onto your IDMT relay. As you can see, these relay here, they got some plug settings. Now these plug settings, they need to be on the correct place. If you've got a couple of them, they cannot all have the same plug settings, right? They need to have different plug settings so that they can have different pickup current and so forth, and the operating time and so forth, as we've already discussed earlier on. Okay, so let's go ahead and just have a look at what we've got here as a problem statement. We've got a radial feeder CBA, okay, that supplies two substations B and A from a source C. Now this is very important because this actually shows us the direction, the flow of the power. Okay, so it's CBA, that's a radial feeder that is supplying to substation B and A from the source C, so which means power is originating from C. The fault level are 1500 amp and 900 amp respectively, and the load consists of 5 induction motors, each taking a full load current of 25 amps. So basically these fault current, they are located on each one of these bus bar, okay, and each taking a full load current of 25 amps. Now this is important because there is a fault current and there is also normal loads that are attached onto the bus bar. Now we're going to draw this bus bar so that we can actually see the layout. That will give us a good understanding of the problem statement. Now let's just finish reading. 3 of the motors are connected to station A and 2 are connected to station B. Now protection is provided by means of a very inverse time over current relays. Now there are a few different type of IDMT relay characteristics curves. Okay, now the characteristics curve also dictate the way in which the IDMT relay will respond to a fault current on the system. Now this is one of the characteristics curve that is called the very inverse time over current relays. Now the formula to calculate the operating time, TC, is given by this formula, 1.6 divided by the log of m square. Okay, now I've got a tutorial where I actually explain all these characteristics of an IDMT relay. Great. Now where T is the time in seconds and M is the multiple of settings. Now there are CTs with ratios of 150 to the primary and 5M to the secondary. I use at both stations, and the motor starting current are 6 per unit each. Now relay plug settings range from 50% to 200% in 25% steps. Okay, so that is the relay plug settings. Okay, now allowing a minimum time of 0.5 seconds for the relays at B, a grading margin of 0.4 seconds, and assuming a pickup at 110% of the settings. Now this statement here is very important. So they're allowing a minimum time of 0.5 seconds for the relay at B. So that is the minimum time for that will take for the relay at B to operate before the relay at A takes over. Okay, and there is also a grading margin. Now we're going to look at all of these statements when we start solving them, and assuming a pickup at 110% of the setting. So now we've got two questions here. The first one is to determine the suitable plug bridge setting, right? So that is the plug bridge settings that I've already mentioned a couple of times here. We need to determine where this plug is going to be moved. As you can see here, it's standing at 0.5. Now it needs to be moved from there to a specific setting, so that is very important. And we also need to find the TMS, that's a time multiplier settings for the relays at C and B. Great. Now the best approach to actually start solving this type of problem is to always draw your network layout. So let me go ahead and bring the layout for this problem statement. That way we can have a better understanding of what's going on here. So as we've said earlier, we've got the radial feeder CBA, and then we've got the source that is coming from C. So the way you have to look at this is that this bus bar or feeder arrangement here, bus bar C is actually the one that is sitting next to a power transformer that is on your incoming line, okay? And then you've got the rest of the bus bar are connected as follows. So which means bus bar C and the relays connected or set up near to this bus bar will be protecting the fault current on the upstream. And the fault level for our systems are 1500 amp and 900 amp respectively. So that is the 1.5 kilo amps on bus bar B and the 900 amp on bus bar A. Now we've also got loads, right? So they say the load consists of 5 induction motors in total, okay? So then we've got each one of the loads having a 25 amps full load current. So that basically the current that will be drawn when the motor will be running, okay? From the 5 motors, we've got 3 motors are connected to substation A here, and we've got another 2 motors connected to substation, and the system protection is provided by the very inverse time over current characteristics. So that is governed by this formula. Great. Now we've got CTs, right? So the CTs are 150 on the primary and 5 amps. So that's our CT ratios. Now remember, these CTs are all located close to each one of these bus bar. Now the interesting thing to note is that this CT here on bus bar C is basically protecting the bus bar B and bus bar A, right? So that's basically how they operate, right? So now the next statement here is the per unit current are 6 per unit. That is the starting current for the motor. Now that is very important, so we're going to look at that when we start calculating. The relay plug settings are provided here. That's basically what we're going to calculate on the first question here, and we have to allow the minimum time of 0.5 seconds. The problem statement, as far as we are concerned, is quite clear to us. Now we can actually start solving by calculating the suitable plug settings for the relays. Now the plug settings, if you walk into a substation or into a network installation where you've got this IDMT relay, if you look at it closely, you're going to see something that looks like this. This is basically the plug bridge. Now here they've said that the plug settings, they will be ranging from 50% to 200% in steps of 25. Now when you look at the physical device, you can see starting for 0.5 and it's moving in step of 0.25, right, and all the way to 2. That basically the 200%. So our calculations is going to give us a value that will be within this range of plug settings. But now when you calculating the plug settings, remember the plug settings are for each one of these relays that is located on each one of these bus bar. Now I have already stated that relay C here, right, relay C will actually be protecting the situations going on bus bar B, and relay B will be protecting whatever is going on bus bar A. So which means the relay A here will be protecting something that is not illustrated in our network. So we do not know what's going on the upstream side of our network layout. So which basically means if we need to calculate the plug setting for this relay based on this problem here, we actually can ignore it because we do not have enough information for us to calculate the plug settings for this relay, because the plug settings are basically informed by the fault current and the load on a specific bus bar that we need to protect. So we're going to ignore the plug setting for relay A. Now we can go ahead and move to relay B plug set. Now when you look at our network layout, we can see that this relay B here need to protect the system on bus bar A. So the load here, we've got 3 induction motors and we've got a fault current of 900 amps. Now it is important that we must set up the plug setting for this relay so that it does not trip the circuit when these motors are running, okay, all the three of them, or whether one is also starting, it must not trip, because that is a normal condition. It must only trip when we reach the critical point of 900 amp fault current. So that's basically what we need to do. So in order for us to set up this relay so that it doesn't trip, then we need to know what is the full load current of this relay. Now the problem statement say that we've got 3 induction motors and running at 25 amps, and we know that the starting current for each of the motor is 6 per unit. So what we're going to do there is to basically calculate first the overload, right? So that is the overload condition that we can accept. Now the overload situation is that you're going to, because each motor is starting one at a time, right? So they're not starting all 3 motors at a time, because if they start 3 motors at a time and each one of them having a 6 per unit starting current, you're basically going to have a lot of current flowing that might actually trip the circuit. So they are starting 1 motor at a time. So which means the worst case scenario is we've got 2 motors already running. That is at 25 amps times 2, right? Plus the 1 motor that is starting, that will be 25 times a 6 per unit current. So we're going to get an overload current of 200 amp, right? So that is a worst case scenario. Then the normal load will basically be the 75 amps. So that basically the 3 motors running. When they all done starting, they basically just running in full load, you're only going to have a 75 amp normal load. Now we're going to set up the plug setting for the overload current so that it does not trip. Okay, great. So to do that, let's go ahead and bring the formula for the plug setting. So formula for plug setting is the nominal current for normal load divided by 0.9 times the CT ratio times the nominal current of your secondary CT. Now I've explained this formula on the previous tutorial. That is why I said earlier, please watch those tutorials so that you can catch up with the pace. Now to get the current for the normal condition of the load is basically we replace the 75 amps current here with 0.9, so that basically the 90% pickup divided by our CT ratio times 5, which is a secondary CT current. Then we can get a value of 0.55 that gives us a plug setting of 55%. So that is for the normal condition. But now we cannot stop there. We need to get the overload condition. Now the overload condition, as we've already calculated the current of 200 amps, then we have to use the pickup setting of 110%. Okay, then that will result in having 200 divided by 1.1 times 150 divided by 5 times 5, and that gives us 1.21, which will give us a plug setting of 121%. But now it is 121%, so we have to select the plug settings higher than the value we calculated. We cannot go lower. Now the next plug setting, we know that is 125%, because it's moving in steps of 25%. So we're going to select a plug setting of 125%. Now I'm going to stop this tutorial here because it's getting a bit long. All right, so I'm going to stop it and then do part 2 so that we can finish off the calculation. Now if you've been following and you've watched the previous tutorial, I'm sure if you apply your mind, you'll be able to actually finish it off and get the correct result. And that is actually a good exercise to try until I release the next part 2 of this tutorial with the solution. So if you find it useful and informative, please give this tutorial a thumbs up and stay tuned for the upcoming part 2. Until next time, cheers.